Today we are starting with a new topic, which is an important topic, and the name of the topic is the magnetic effect of current. So what will you learn in this particular topic? See, the chapter itself means magnetic effect of current. So obviously there is an electric current flowing in a wire. What does this electric current produces around it? You have done this in 10th standard also, and the scientist Oersted, in his experiment, he found out that if you have a wire and the current is flowing through this wire, then let's say that the current is flowing across this wire AB, then there will be a certain magnetic field around it, and this magnetic field what is around the wire has a particular direction, and due to this magnetic field there are certain consequences about this magnetic field. That's what we will be learning in this chapter. So Oyster experiment, you know this, that since the current will be flowing in this direction, if I place a magnetic needle over here, it will deflect in one direction. If I change the direction of this electric current, then the direction of the magnetic field will also change. So what does it indicate? It indicates that moving charges produces magnetic field in the surrounding space, and these moving charges, when their directions are changed, the direction of the magnetic field is also changed. Now what are the moving charges over here is electron. So these moving electrons with a higher velocity produces some magnetic field around it. So it's very important point. What you already know is that moving charges always produces the magnetic field, and we denote magnetic field as B bar now. So moving charges will produce the magnetic field, and one of the important idea which was put forth by a scientist, and the scientist name was Biot, and the other scientist was Savart. So Biot-Savart, and they came up with a certain law, Biot-Savart law. And what did they came up with is that, let's say that I have a wire, and let's say that I have a wire of arbitrary shape, and let's say that this particular wire, the current flowing is I. So if I am talking with respect to a small part of this wire, let's say I am talking with respect to a very small part of a wire, and let's say that I take this, a dot, which is very small part of this wire. Now if you look into this part, the current is flowing across this point. So let's say that this particular small element, let's call this as dl bar, and since the current is flowing across this, the total will be I dl bar. This is called as current element, and this is nothing else but it's the vector quantity, and we'll be using a word element henceforth for this. So I dl bar is my current element, which is very small as compared to the length of the wire. And if I'm talking with respect to this particular wire, and I'm talking with respect to a very small element, then we will find the magnetic field due to this small current element, and the magnetic field due to this, let's say it's somewhere here, and the point is, let's say P, and there is another point, let's say this is P dash, and let us say that these 2 points are inclined at an angle theta, and r bar be its position vector. So the same thing happens over here. Let's say that this is P dash, and the angle formed over here is theta, but for time being we'll consider only this as the theta, and we have a current element I dl. Now it's very important that the magnetic field which is produced at P and P dash, they have a direction. And how do we find the direction? We find the direction of magnetic field by using right hand thumb rule. And if you don't remember, I'll just give you an idea that what is this right hand thumb rule. You grab a current carrying conductor in your right hand. It's like this. You grab a current carrying conductor in a right hand. Let's say that this cap indicates the direction of the current. It's in this direction. I hold this conductor this way. That is, the thumb indicates the direction of the current. Then this curled finger will denote the direction of the magnetic field. So if this is my conductor, current is flowing this way, and I curl my finger, then my fingers at point P is going inside. And if I imagine, these fingers will go somewhere here and will come upward. So that means the field at point P is going inside, and we show this with the cross mark. That is, field is going inside the page. And at this point the field is coming outside, so we show with a dot. So we have a cross which indicates the field lines are going inside. We have a dot indicating the field lines are coming outside. So hope you have understood this. So let's say that dB bar is the magnetic field at this end. Then dB bar will be the magnetic field at this end too, because we have taken this position vectors equal. So we have to find the magnitude of field at point P. So Biot-Savart Law says that magnetic field at this point is directly proportional to I dl bar cross r bar upon r cube. The statement says that the magnetic field produced at point P or P dash is directly proportional to I cross product of dl bar cross r bar upon r cube. They have removed this constant of proportionality, therefore this transforms into dB bar equals to mu naught upon 4 pi I dl bar cross r bar upon r cube. This is the equation, and this is in a vector form. This equation is in the vector form. I can convert this into the scalar form also. I just convert this given cross product, like we know formula for A bar cross B bar, it's AB sine theta. So I apply that logic over here and we get the answer. So if I convert this into only the magnitude, I get this as dB equals mu naught upon 4 pi I dl dot r dot sine theta upon r cube. One r from here and here gets cancelled, so my final answer will be mu naught by 4 pi I dl sine theta by r square. Whereas theta is the angle between the current element, that is I dl, and r. So theta is the angle between the current element and the position vector r bar. Now this was dB bar, that is the magnetic field at point P. If I want the magnetic field due to the whole conductor at point P, what we do is that it's B bar equals to integration of dB bar. We just integrate this and we get the magnetic field due to the whole conductor. That is the resultant field at point P.